Okay, so it's my great pleasure to introduce Professor Samuel Chancet from Université Catholique de Leuven in Belgium. So Samuel is the core developer of the EPW package for electron-phonon coupling, which is one of the most popular packages for this. And the title of the talk is Electron-phonon coupling from First Principles. Samuel, the floor is yours.
Thank you very much, and also thanks to the organizer for this very nice school. So basically, yesterday you saw a lot about the electrons, and just now you saw about the phonons. And so what I'm going to try to do today is basically bridge those two things together. So you have this collective oscillation that we just saw, and then we have this concept of electrons. So typically you decouple them, you use the bond splitting, and so you can see them in somehow living in static ionic potential. But then if you start to look at them, and maybe the best way or the best direct way is called ARPES, so angle resolved photoemission spectra, in which you can see sort of the energy of the electrons as a function of their momentum. And so this is really a powerful technique. So how does it work? You shoot sort of photons on a sample, and then thanks to the photoelectric effect, the electron will be extracted from the sample, and they will be extracted with a certain angle and a certain energy. And so by recording that energy and that angle, you can reconstruct the band structure that you are computing with DFT and so on. So you really have like this beautiful 3D maps of the energy as a function of the momentum of the electrons. And so what you notice is that the bands are not they're not lines; they are sort of a line width, and so this line width are due to sort of lifetime of the quasi-particles, and they are due to electron-phonon, they are due to phonon. We will see after the coffee break. But what is really nice is that this is maybe the most direct observation that we can make. And now, if we want to talk about electron-phonon, I will show direct manifestation of that effect. And so one of them is that in metals or heavily doped semiconductor, what happens is that you have the emergence of kinks. So you can really see them in ARPES experiment, in which you have this sort of small kink close to the Fermi level. So if you know the sort of Baire dispersion, and there are different ways, you can simply use a parabolic model, or you can do a DFT calculation that doesn't include the coupling between the phonons and the electrons. And this is sort of your Baire dispersion. And sort of by definition, the measured dispersion is equal to the Baire one plus the real part of the electron-phonon separation. And so by looking at this kink and measuring sort of these differences, you can extract or reconstruct what the electron-phonon coupling is. If you are in materials where you have a very strong electron-phonon coupling, or you are at the sort of band edge, then again, using this ARPES technique, you will see the appearance of these sort of satellites or band replica. And you can notice that they are splitted by typically an optical phonon away of each other. And those are measured of large polaron. And so recently, one has developed tools to describe this large polaron, but using only the information on the primitive cell. Another manifestation of electron-phonon coupling is the band gap renormalization. So again, if you neglect the interaction of electron and phonons, you have the Baire band gap. So this is the DFT or GW band gap that you obtain, but in reality, the measured band gap is typically smaller. So you reduce the band gap due to electron-phonon interactions. Notice that even at 0 Kelvin, you have an intrinsic vibration of your atoms. So this is the h bar omega over 2. And this is called the 0-point renormalization. And this is the case of diamond. So in diamond, this is very strong. So you have something like maybe 0.5 EV renormalization. So if you neglect electron-phonon coupling, you are overestimating your band gap quite significantly. And then as you increase temperature, you sort of excite more phonons and so on. And then the band gap is decreasing even further. And again, it's possible using linear response theory to compute this effect, so the band gap renormalization in semiconductor. Something very important, so for solar cells, So the issue is that light has almost no momentum. So when a material absorbs light, you're doing basically direct transition. This is momentum, this is energy, and this means that actually the direct band gap of silicon is 3.4 eV. So this means that if you have only direct excitation, you would only be able to absorb light only this very small part of the spectrum. So this is the sort of solar spectrum at sea level, and you would only be able to extract a very small amount of energy. But actually through the interaction between the photon and phonon, so if you have both interaction, then you're actually able to do an indirect band gap transition. So this is called phonon-assisted optical transition. So you're using the momentum from the phonon and the energy from the photon in order to make this transition, and therefore you're able to absorb a much larger fraction of the spectra. And this is why silicon is actually a very good it's used for photovoltaic, and it's very good in that way. Notice that in that particular case, because you need both a photon and a phonon at the same time, typically you need quite thick layer of silicon in order to be able to absorb. In contrast, if you have a direct band gap materials, then you're able to also absorb light, but in using much thinner materials. And this is the sort of excitement around perovskite, for example. So perovskite usually have a direct band gap, and this allows you to have very thin material for absorption. Another example of electron-phonon coupling is for example, for LEDs. So what you're doing here is relatively similar. So you have a photon, so you have like a light source, like blue diodes. Some of the light goes through, and then here you have this, so it's called phosphor absorbing material. And so some of the light will get absorbed, like here. And then due to interaction with lattice, basically what happens is that the electron will relax to the minimum of the conduction band, and we lose some of the energy as a form of heat. And the result is that then the electron will emit another photon, but that way the photon will have longer wavelength, and so you're losing some of the energy. And effectively what is happening is that you're transforming blue into green or in other color. And by having different layers of phosphor, you can give the impression of white light. So by combining them in a good way, you can do white LED for light application. And so the difference of energy is called the Stokes shift. And again, this is something that one can compute ab initio. Something that was mentioned by Professor Ginozzi was the fact that also electron-phonon coupling is responsible for the standard phonon assisted sort of superconductivity. So here you are creating Cooper pair, and then they can travel in the material without resistance. So you have two effects in the case of, at least, in the case of superconductivity. One is the fact that the magnetic field line get expelled, and this is explained by the Meissner effect, or the fact that you have levitation train. And the other very nice thing is that when you go below the critical temperature, then the charge, the electron, can travel with almost zero resistance. And finally, the last manifestation that I want to talk about is mobility, or the transfer of electric charge. So when you apply an external electric field, you will start to make the carrier move. And so this is Joule heating, and what is happening is that the sort of velocity at which the carrier travels in the material will be reduced through the interaction in the lattice in which they are propagating. And if you're increasing the temperature, basically what is happening is that you're reducing that mobility, because you are increasing all the collision with the lattice. Okay, so all of the one I presented, it's possible to compute them using typically perturbation theory. In this talk, I will focus on the last two. So I will talk first about mobility, and then I will touch a bit on superconductivity, and those will also be the two exercises that we will do this afternoon. So I will not go in all the details, but I just want to give a flavor on the fact that you can really derive this from a very general Maliboli framework. So this is the current density that's expressed, you can express as a function of the Green's function. So this is the propagator. And there, if you want to then compute the current density, you have two strategies. You can go the linear response way. And so this is the Hubbard formalism. This is resting on what is called the fluctuation dissipation theorem that we saw yesterday, which is connecting a non-out of equilibrium process with equilibrium quantity. So the fact that you have fluctuation, even at equilibrium, is connected with dissipation, meaning going out of equilibrium. And so this is one strategy, which I will not talk too much about, but another strategy is to rely on Green's function, because we know a lot about Green's function, we have a lot of machinery, and so you can express this Green function in terms of field operator, then you can deal with them in a contour, you can do a Taylor expansion, you can use Wick's theorem, and so on and so forth, which allows you to have basically a pair of interaction, and then you can express this in form of a Dyson equation, and then you can solve that Dyson equation using this, and you can obtain what is called this is one of the Kardanov-Bain equation of motion. Okay, and so up to here it's fully exact. So the difference between going the Kubo way is that you first do the linear approximation, whereas here we are still let's say exact, and then we will do a series of approximation. So what is this equation describing? It's basically describing how this Green's function is changing, how is it evolving in time. And you see that we have these three components. So we have one, which is the unperturbed time evolution in a static potential. You have one that we call local time self-energy, simply because you have only one time. And then all these four terms are connected with all the sort of correlation, collision, scattering, and so on. And so here we are exact, but then we can do very well defined approximation to end up with something we can compute, which is the Boltzmann transport equation. So I will not explain all of them, but they are in this review. And so if you do all of this approximation, also you are considering now something that is time independent, so you are in a DC type transport, but one can also do the time varying one. Then you end up, after all this simplification, with what is called the Boltzmann transport equation. And so what is this thing explaining? So on the left, you have the driving term. So this is the electric field that is pushing your charge. And on the right, you have all the collision, everything that is resisting towards this pushing. And so in steady state, you want to equate them. So you want that all the driving terms are equal to all the resistive terms that you have in your material. And so here on the right-hand side, you see the electron-phonon matrix element that was introduced just before. And then you see those four terms, and those are energy-conserving terms. And they describe the fact that you can get in and out of this state F and K by either emitting or absorbing a phonon. So F is this out of equilibrium occupation of the state. And then basically you have the phonon frequency, and you have this electron-phonon matrix element. But so the important part I want to stress is the fact that the Boltzmann transport equation is often referred as semi-empirical, and maybe that was how it was developed initially. But I want to make a case that since you can really derive it and there is no empirical parameter, this is really a sort of an approximation, but I wouldn't say that it's really empirical in a way or semi-empirical. Okay, so now that we have a way to solve this occupation function, we can then come back and try to compute the current density. And so the current density, so if you want the Green's function, you can block project it and obtain this occupation function. And so now what we are going to try to do is to how to compute this object. In the case of weak electric field, we do again linear response, but you see that we do it at the end, in opposition to Kubo, in which we start by doing the linear response to the current density. So by definition, the conductivity is the change of the current density as a function of the external electric field evaluated in the limit of vanishing field. And so what you have is you have the V, so this is the carrier velocity, and then you have this change of the occupation with respect to an external electric field. Now, often it's convenient to use mobility instead of conductivity because the conductivity will scale with the number of carriers. So what you do is you simply compute the conductivity and you divide by the number of carriers that you have in your material. And so this is called the drift mobility. So the way to compute this, you have the drift mobility, the velocity, and then you want to obtain this, and you can obtain this change of occupation by solving this Boltzmann transport equation. Now you can see that there is a small issue. If you want to compute this dF, dE as a function of f, you see that you have it here, but you also have it here. And it's basically the same, but at k plus q. So in order to solve this, one way is to solve this iteratively. So you simply start with an initial guess. Typically, you kill this term. So this is the initial guess, and then you do a self-consistent loop until those two terms don't change. I have also highlighted this tau. This is the scattering rate of the line width, and it's connected with this object here, which is actually the imaginary part of the electron self-energy. So there is a connection to the self-energy, and this is why one can, if we decide to not solve this iteratively, we can just, and this is an approximation, we can just kill this term, and then we have what is called the self-energy relaxation time approximation, because it connects your mobility directly to this lifetime or scattering rate. Okay, so this is very good. Now we want to compute this in practice. Now the issue is that, sure, we can compute this electron-phonon matrix element, but we have to do this DFPT calculation. This is very expensive. And the issue is that you have this term, for example, so this is one of the problems, is that you have the change of occupation as a function of energy. Now, F0 is the equilibrium occupation, so this is the occupation if you don't have an electric field. This is simply the Fermi-Dirac distribution function. Now, if you derive this with respect to energy, it's an extremely peaked function. So here I'm showing the function, here as a function of the energy, and you can see that this is only 0.2 eV, so you are at the edge of the valence band of diamond, or the edge of the conduction band of diamond, and you can see that basically this term will only contribute extremely close to the band edge. And so for this reason, you need very, very dense K-point and Q-point grid in order to converge that calculation. And so this makes it extremely difficult to compute because you need extremely dense K. And so one strategy is to rely on exactly what was shown in the previous talk, is to rely on interpolation. So you can interpolate, and we saw that just before, you can interpolate the interatomic force constant, the dynamical potential, sorry, and we can also interpolate the electron-phonon matrix element. So the strategy is that you compute those objects on a coarse grid, you remove the long-range interaction, you do a Fourier transform into real space, and then you do an interpolation of these quantities, so both the dynamical matrix, but also the electron-phonon matrix element. And this is much cheaper. This is the idea behind the EPW code. Okay, but so what is very important is to have a good description of the long range, because you need something that is localized in real space in order to do an accurate interpolation. And so this was basically, so the electron-phonon matrix element was introduced just before by Professor Giannozzi, and something I haven't mentioned yet, but we are actually doing this in a Wannier framework, and there are some advantages for that. And so here you see actually this Wannier transformation that we saw yesterday. So one of the reasons is the fact that Wannier functions are smooth in reciprocal space. So here what I'm showing is the real part and the imaginary part of the electron-phonon matrix element for the band 1,1 for a specific material, and I'm showing this as a function of Q momentum. And so we saw yesterday that there was a phase randomness. So for each Q, you're doing one DFPT calculation, and you get a random phase. So this is completely random. It's not so nice. But then if we simply do this rotation in a maximally localized basis, so we're using these U rotation matrices, then suddenly the electron-phonon matrix element is very nice. So just by doing this rotation, we have something that is smooth, except at Q equals 0, where you can have a divergence, but everywhere else in the Brillouin zone, you have something very smooth. And so this has nice properties. Also, you want something that is localized in space in order to do the interpolation. And so this is the reason why we are actually transforming our electron-phonon matrix element in a Wannier framework. So now what we are doing is we would like to separate our electron-phonon matrix element in a short range and a long range form. And here I've just explicitly wrote this Wannier rotation. And then here you have this long range potential. So this is the change of the potential when I'm moving my atom. So how does my potential change here if I'm moving the atom over there? And so in order to do this interpolation, what we need is an analytic way to express this long range. And so this analytic expression exists. So you have some formula for 3Ds. So this is the long range, and you can see that you have this F function. So this is a range separation function. It's used to separate short range from long range. So this is an exponential, and you have some sort of length that helps you for the conversion. Then you have this multiple expansion. So we talked about, so this is the Born effective charge, but you also have the quadrupole. So this is the dynamical quadrupole. And I'm stopping here at second order, but you can also continue octopole and so on. Then you also have a term which is R dependent. And so this is due to the change of the exchange correlation functional when you apply an external field. And finally, in the denominator, you have this sort of extension of the dynamical, the electric function. Okay. Now you have the same similar expression, but in 2D, they take a more complicated form. Now this range separation function, instead of being an exponential, is an hyperbolic tangent, so it's the same idea. And again, you have this multiple expansion, but now you split that into in plane and out of plane. And then you also have to compute the optimum sort of length scale for doing this range separation function. And this is some example for somebody here. Something that is very specific to working in a Wannier framework and working in a framework in which you are interpolating the electron-phonon matrix element. But there are actually other ways to do this. You could also interpolate the potential instead of the matrix element. But if you're interpolating the potential, something that is happening is that the way you express this periodic part of the block function in the Wannier basis is that you do a Taylor expansion like this. And what is happening is that the part that is depending on R will get an additional term. If you go to second order, you will have this derivative of the periodic part as a function of momentum that will be sandwiched, with the state on the other side. And so what appears is this Berry connection. So somehow you have a Berry connection which is appearing when you're doing this Taylor expansion. So this has only been recently discovered, and it's actually important if you want to go to second order when you do this long range expansion. So one way to quantify how good this interpolation scheme is to look at the deformation potential. So the deformation potential is a way to probe the electron-phonon matrix element. So here I'm showing the deformation potential of SNS2 as a function of Q, and you can see that it interpolates very well. So what is happening is that the lines are computed on a very coarse grid. So only a few Q points in the grid, and then you do the interpolation and you obtain these lines. Instead, all the dots are independent direct DFPT calculation just to verify that we are interpolating, indeed correctly, and you can see that it works quite well. On this scale, you have the optical mode that dominates, so you don't see much. But basically, I'm showing the interpolation done with only dipole, so dipole term, and the one including dipole and quadrupole. If you zoom in, so this is another material, but it's the same concept, it's MOS2. If you zoom in, you can see that there are some small differences. So for example, those are the out-of-plane mode. And if you only include dipole, then you see that you don't recover the exact dispersion, okay? I just want to mention a small point because this will be used in the tutorial. So you see that in addition to this change of occupation function, you have this velocity. So this velocity is very important to compute accurately if you want to compute the mobility. And there are two ways to compute this also in the code. So you can use the commutator that we saw before. So this is an exact way, has some advantage. Or you can actually compute the velocity from a Wannier framework. So one can show that the velocity is the Hamiltonian, and then minus this term, which itself can be expressed in the Wannier framework in terms of the overlap that we saw yesterday. So this M&M matrix that you had in the Wannier 90 code. So this is the overlap between a block state and the neighboring one very close to it. Both give the same result, but only in the limit in which the Wannier functions are converged. If the Wannier functions are not converged, then actually the previous way is more accurate than this way. Okay, so now we've shown how to compute this and pay attention to the long-range thing. Then how does this work? I mean, does it work well with experiment? So here I'm showing actually 10 materials, so very simple one, diamond, arsenite, and so on. Every time I'm showing the electron mobility and the hole mobility as a function of temperature. And I'm comparing to experiments. And you can see that the agreement is relatively good, even though for some materials we don't have experimental data or very few experimental data. What is nice with a sort of general framework like this is that you can also understand the microscopic origin for this mobility. So this, what I'm showing here is the spectral decomposition. So what it means is what are the phonon modes, so this is the phonon frequency, what are the phonon modes that contribute the most to the scattering, so to the lowering of the mobility. And you can see that it's very material dependent. So for sort of stiff material like diamond, cubic boron nitride and so on, you really have acoustic scattering dominated, while for materials like gallium arsenide, aluminum arsenide, and so on, you have optically scattering dominated. But so in principle, you cannot know in advance, and so it's very important to include all the possible scattering if you want to be predictive. So you can also see that there are some materials in which both acoustic and optical are important. If you compare to experiment, you have here the calculated mobility versus the experimental one. And so if you are on the line, it's perfect agreement. Note that this is an logarithmic scale, and so exponential scale, and so basically the dashed line are a difference of a factor 2, so it's 100% differences. So you can see that in many cases we overestimate experiment, and this is actually expected because here we have only included the interaction between the electron and the lattice. But actually, you have other scattering mechanisms. You can have ionized impurity scattering, defects, and so on. So when you are comparing to experiment, you always expect that you will overestimate with respect to experiment. And in fact, you can see that here you have some underestimation. So this is not very good. And the reason is simply that we are using this self-energy relaxation time approximation. If we do better, and we are doing this iterative solution of the Boltzmann transport equation, then we are starting to overestimate as we would expect. But actually, what we are doing is the drift mobility. But in experiment, what is often done, because it's simpler, is to use the Hall effect. So in the case of the Hall effect, you apply a magnetic field, you are measuring the difference of the potential. So what is happening is that you have the sample. In addition to the electric field, you apply a magnetic field, and then due to Lorentz force, all the carrier will be deflected on the side of your material, and you can then measure the Hall potential. Now, the issue is that this magnetic field will be an additional driving term, so you need to take that into account if you want to be predictive. And so you have that the Hall mobility is the drift mobility multiplied by this Hall factor. So this Hall factor will have an effect on your mobility. And so what we can do is we can just go back to our Boltzmann transport equation, and as before, on the left-hand side, you have the normal term, and then you have an additional term due to this additional driving term, which is simply this magnetic field. And so what we are doing is we're actually computing this with at finite small magnetic field, and then we can solve again this Boltzmann transport equation, but now including magnetic field. And so if you do that, you then obtain what is called the whole Boltzmann transport equation. And you can see that now, in this case, we are really overestimating all the time up to a factor 2. So we are somewhat predictive, but we are always sort of overestimating, which is what is expected. I want to mention that the Hall factor is something relatively complicated. So it depends on temperature. It also depends on, sometimes it goes up, sometimes it goes down, sometimes it's flat, and also it's not 1. So in many textbooks, it's assumed that the Hall factor is independent, it's basically 1. And so often the drift mobility is the same as the Hall mobility, but you can see that it's not. So it's very important to compute the Hall factor in order to compare with experiment. Now, like I mentioned, there are different scattering mechanisms. Now I've dealt only with electron-phonon, but you also have carrier impurity scattering. This is very important. If you start doping your material more and more, you will have basically interaction between the carrier that is propagating and the other excess carrier that you have in your material. If you do quite serious approximation, it's then possible to compute ab initio this impurity scattering using only the primitive cell. So you would expect, okay, if I'm putting some carrier, I should do a supercell, putting more charge. But if you do all this approximation, you are in the dilute limit and so on, then you can express your impurity scattering rate with this approximated formula. And so it works quite well, at least for silicon. So this is the case of silicon. And as you can see, this is the result with only phonon. So this is what we showed before compared to experiment. But now if I'm increasing the amount of charge I'm having, so 10 to the 16, 10 to the 17 dopant, then what is happening is that the mobility is decreasing, which you expect because you are putting more scattering. So this is at room temperature. You can see that here I'm in this intrinsic limit, which is flat. And then basically I'm reducing the mobility due to this additional scattering, and we can do that as a function of temperature or as a function of ionized impurity density. One thing that is interesting is that then we can assess what is the validity of the Mathison rule. The Mathison rule is extremely widely used, and it tells you that you can basically separate the phonon and the ionized impurity contribution. So you can say that the inverse mobility is equal to the sum of the phonon limited mobility and the impurity limited mobility. And so here you see the decomposition. So this is the phonon limited mobility. You remember, if you increase the temperature, the mobility is going down. Instead, if you increase the number of carriers, actually the mobility is going up. So this is the impurity only term. And then if you use Mathison rule, you get this dashed line. Okay. But in reality, if you then do the calculation by putting the impurity in the iterative Boltzmann solution, then you have some coupling between the this impurity NK term and then also the phonon limited one, and you obtain this full line. So what you can see, because again this is a log scale, you can have up to a factor 2 differences by using the Mathison rule or computing them exactly. And this is temperature dependent. So the largest difference is around room temperature, and then in one or the other limit, it's more it's closer somehow. So in a way, it shows that there is some limitation to the Mathison rule. Okay, so this is sort of the first part. Is the first part on the mobility. And so now I would like to touch briefly on also superconductivity, since we're going to do some exercise in the other session. So the slide have been given to me by Professor Roxana Margin, and she was also the one who implemented this Migdal-Liège-Bert theory in the EPW code. So many thanks to her. So the superconductivity. So this is the sort of phenomenological original BCS theory, in which you are forming Cooper pairs. So you have two electrons that are interacting via a phonon, and once, that basically creating this sort of quasi-particle picture, and those below the critical temperature, they can travel with almost zero resistance. So what is happening also is that here you have the density of state, you are in a metal, okay, so you have the Fermi level, and once you go below the critical temperature, you are actually opening what is called the superconducting band gap. And okay, is this one? No. Speak Italian. Okay. Okay, so you can see that here you have this expression that describes the superconducting band gap as a function of temperature. And so this is the value at zero Kelvin. So this is the superconducting band gap at 0 Kelvin. And if you increase temperature, basically the superconducting band gap goes to 0. And when it reaches 0, this is the critical temperature at which you lose the superconductivity. So it works relatively well. It describes this phenomenology of superconductivity, but it's actually material independent. So you can see it because at 0 Kelvin, at least, you have a direct relationship between the size of this band gap and the critical temperature of the materials. So this means that two different materials that have the same critical temperature will have also the same band gap. And obviously, this is not the case. So different materials can give you different superconducting gap. And also, it doesn't account for retardation of the electron-phonon interaction. And so the idea is to go to maybe a more refined theory. But staying to this sort of phenomenological theory, I just want to mention that also this is a very used formula to compute the critical temperature. So this is called the Macmillan-Allendale formula. And it's quite easy. It allows you to estimate the TC. And the only parameters that you need is the electron-phonon coupling strength. So this is just one number. And you obtain it by taking the sum or the integral over the Fermi surface of the electron-phonon matrix element, weighted by the phonon frequency. And you do this only on the Fermi surface, and you get one number that you can plug in this formula. You have this empirical Coulomb potential. This describes the electron-electron interaction. And then the omega log is a weighted phonon dispersion. But again, it's just one number. So this is easily calculated. You get it from the output of quantum espresso, and so on. It works well for isotropic superconductor, but it has some limitation. So since it's only an integral, you have no resolution. So for example, if you have anisotropic superconductor, you will not describe them very well because it's just one number. And then also this Coulomb interaction is approximated with one number. Okay, and so what can we do to improve this? And so one of the important development is this so-called Nabu-Gorkov formalism, in which you are extending the normal Green's function framework to deal with anomalous Green function. So instead of having one, you now have a 2x2 matrix, and on the diagonal, so here you have your creation annihilation field operator, but now you also have off-diagonal one that describe this anomalous transport propagation, if you want. Yeah, so basically the diagonal of this sort of generalized Green function is the normal state Green function. So those are the ones that describe all the properties that we had before in Green's function. So for example, for transport, and to describe this single particle excitation or the propagation of a single particle. While the off-diagonal are called the anomalous Green's function, and they are actually responsible for describing the Cooper pair, so these superconducting mechanisms. You can expand them in a Fourier series, so you can basically now move to this imaginary times, and so these are basically called Matsubara frequency, and they are linked with the temperature. So the lower the temperature, the more Matsubara frequency you will need, and you will see in the code that this is actually one of the limiting factors. So if you go to very low temperature, calculation becomes very expensive because you need many Matsubara frequency to describe them. Okay, and so we can then look at the electron-phonon self-energy, but this is a bit generalized because you have this Cooper pair, so it's actually called the pairing self-energy, and it has the usual fan term, that is the same for the normal electron-phonon. So this is the dressed phonon propagator, this is the electron, and then the G are the electron-phonon coupling. But you also have a screen-Coulomb interaction. Yeah, that describes this. Okay, so basically we can express this pairing self-energy in terms of our Green's function. Now we have these polymatrices because remember it's a 2x2 matrix, and so we have basically the sum of those two Feynman diagrams. So we have one that is the fan electron-phonon coupling, and then we have this electron-electron. So one can do some approximation now. If we want to compute this, we can use, instead of the full phonon propagator, we can use the pair phonon propagator. That's much simpler expression. And also, just to simplify the equation, we can define an anisotropic electron-phonon coupling. So this is a generalization of the lambda that you saw in the Macmillan-Allendale theory. So now you have this lambda, but now it's momentum, both electron and phonon momentum resolved. And you see that we have this term, which is here. And so if we do this and this, you can basically have a much somehow simpler expression. So you have, that is the same. This is basically the Green function. Then you have this anisotropic coupling strength. And then again, you have this electron-electron. Now, without loss of generality, it's actually possible to split this equation into three scala. So at this stage, we don't know what they are, and it's not well justified why we are doing this, but we can do it. You can think of this in a way as in linear algebra, you can do this singular value decomposition. So you have a matrix, and you can always express it without loss of generality. You can express it as the product of three simpler matrices that you can deal with. So it's a bit the same idea, where you have this sort of complicated equation, and you can split it into three functions that you don't know what they are, but then we will see that they are connected to some physical quantity. Okay, so we are just basically defining them, and now we would like to know how to compute them and how to map them to the exact sort of solution, or exact to the solution that we have here. And so the way to do this is to use the Dyson equation. The Dyson equation links the Green's function to this pairing self-energy via this with this bare Green's function. And so if we plug in this separation, that we don't know yet what it is. We plug it in here, we solve the Dyson equation, and then we obtain, so we do a matrix inversion, and then we obtain this equation, in which in the diagonal you have this z term, this chi term, and then this gap term, okay? And you also have this, which is defined here. And what you do is that then you just take this formula and you map it with this one, okay? And by mapping the component, you then end up with these three equations. So those are the one that maps the one, I mean, these three parameters that we have introduced to the, the Green's function and the self energy that we have in the theory. And so now what we are trying to do in the code is then to solve self-consistently, to solve these linear equations that are connected to each other. And so this is called the full bandwidth, and it's implemented in the code. It's relatively complicated because you have many connected equations. Now we can simplify this. Yes, so on the imaginary axis, and this is called this Fermi surface. So what we are doing to simplify is we are assuming that all quantities are evaluated really on the Fermi surface, whereas here there is actually some thickness. So you're accounting for all the thing that is happening close to the Fermi surface, but also a bit above and below. So this is more general, and this has been implemented more recently. But traditionally, to simplify this, what you do is that you are considering that everything happened exactly on the Fermi surface. And this simplifies the equation because this vanishes when you integrate on the Fermi surface. And so instead, you only have two equations to solve, so it's a bit easier. And so this is called this Fermi surface. Yeah, I don't remember the articles for, but okay. Anyway, so yeah, in practice, this is also what we can solve in the code. Note one thing, you still have this term, which is this Coulomb potential, and this is still one number somehow. And so in the code, you will have to give this number. It has some typical value, but it's something that you have to input to the code. However, one can actually compute this, and you can use codes to compute this electron-electron potential and interaction, and then you can plug that in here, or you can keep the generality, and this hasn't been really done, but you can basically compute the full one, the full result, put it there, and then try to solve it. Okay, so basically this is a very all the equation that we have. And so by looking at the poles of our Green's function and by computing this gap function as a function of temperature, so you can see that here we have some dispersion because this is really a band and momentum resolved object. So you can plot this as a function of the temperature, and when this superconducting band gap goes to 0, then you have the critical temperature. Now, what is also interesting is that here, this is MDB2, and it's actually a multi-gap superconductor. So you can see that you have two band gaps, and they are actually, the two band gaps are on different parts of the Fermi surface. So the Fermi surface is quite complicated. You have this sort of tubular structure, and one of the gaps is in one, and the other is in the other one. And so if you want to be able to describe things like MGB2, you really need a sort of anisotropic description of the gap. Otherwise, you cannot really have only one gap that describes this two-gap structure. Okay. So, yeah, in conclusion, the electron-phonon interaction is very crucial to describe many phenomena. So I have shown 7 at the beginning, but there are also other. The Boltzmann transport equation and the Migdal-Liège-Berg equation can really be obtained from a rigorous many-body framework, and then you do very well-defined approximation. I think that's quite important. In general, the long-range electrostatic is important, not really for the superconductor because you are dealing with metals in which you don't have long-range electrostatic, but for semiconductor, insulators, doped semiconductor, slightly doped, then it's important to describe the long-range electrostatic accurately if you want to do accurate interpolation. In general, the whole factor is temperature dependent and can deviate from unity, so it's important to always account for it. And then here we've shown also that the carrier impurity scattering is important whenever you have some significant doping of the material. Okay, thank you.
Thanks, Sandro, for the really nice talk. It's more regarding a curiosity about these 7 sort of properties that are super cool and interesting that you said that electron-phonon companies actually plays, I mean, most important role there. And it's more regarding the current status. Could you directly address them with the current implementation of the PW, or for some of them, do you need special like further treatment in anything else?
So they're all the 7 I've shown can be computed with TPW with one caveat, which is this one. So this one, the issue with this one is that the renormalization of the band gap is directly linked with the real part of the electron-phonon self-energy. And you can show that this real part has 2 terms. One is the phantom, so this is the Feynman diagram that you've seen, but there is actually another diagram, which is the Debye-Waller. So the Debye-Waller is a second-order derivative of the potential with respect to 2 atomic displacement, but then you sandwich that with 2 unperturbable functions. This is as opposed to one first-order wave function and first-order potential, but they are at the same order. And this is a static object, so it's actually real. And so when you are looking at things like the imaginary part, so the line width and so on, you don't care about that term. But in this case, the real part is very important. And the issue is that to compute that term, you usually need an infinite number of empty states. So you can use the same trick as for perturbation theory. You can recast this as a linear equation, and you can do Stern-Hammer to compute that. But since we are in a Wannier framework, it's actually difficult. So I should mention that actually relatively recently, in Korea, in the group of Shewal Park, they have done some development to use perturbation, to use basically this Stern-Hammer equation in a Wannier framework. So it's called Wannier function perturbation theory. And in that case, you can actually compute accurately this term. But this is not in the public version of PW, but yeah, it will be hopefully in the future. But so apart from this one, but basically, actually, there is the implementation in the Stern-Hammer way without going to the Wannier framework, and this is directly in Quantum ESPRESSO. So actually, you can now do this calculation in Quantum ESPRESSO. The theory behind is called Allen-Heine-Cardona theory, and this is implemented, and you can use it. It's implemented both in Ab initio, in Quantum ESPRESSO, and maybe in other codes. But all the other, so this is in PW, it's possible to do. This is not directly, but you can also do it. Typically, one uses, for this thing, one uses delta SCF that we saw yesterday, because for this, you usually have, you see, actually this, it's some dispersion, this is a 5D state. It's actually quite localized. So the way this works, this phosphor, is that you have, you're doping the material with rare earth, typically, so europium, whatever, cerium. And so what you're doing is you're doing a 4F to 5D transition of this dopant, okay? And so those are localized in the band gap. And so you're trying to sort of compute the Stokes shift of that localized object. And so there it's easier to use basically delta ICF. So you're constraining the equation, relaxing, and then you can compute the Stokes shift and things like that.
Good. Other questions?
You show some result of MGB2. Can you just with the last slides?
Yeah. Yes.
So basically, you have a PC of the.
Yeah.
What I was wondering is that MGB2 has 39 Kelvin, and this is sort of seems to be overestimated,
yes.
But still the new study is quite high with respect to the typical value. So basically, if you decrease the new study, you would go.
Yes, that's correct. That's correct. Yes, yes, yes.
So do you have a comment on this overestimation or?
Yeah, this is relatively common for this this theory to overestimate. Now, how much it depends. I think what is nice is that this typically overestimates the TC, while maybe the Allen-Heine one typically underestimates it, but it's not always the case. But then you can sort of sandwich where you are. I should mention that there is another theory which is called SCDM, I think, from the group of Arvid Groth and so on. Yeah. And it's a sort of different way. I think they also overestimate, but maybe differently somehow, maybe less, I don't know. But yeah, it's quite, I think this case is quite strong. So we also tested other material and we overestimate maybe less, but it depends. So I don't have I don't have a rigorous explanation why you should always overestimate. In fact, I don't think it always overestimates.
But your studies,
Yeah.
you calculated in the previous formula, or you just?
So this is a paper from 2013. So this was the original implementation. I think they just put that because it's known that typically between 0.1 and 0.16 that reasonable value. And indeed, this is the highest reasonable value, it's the token, so I guess. But you could increase it, of course, to reproduce, but okay. But since then, they have done some calculation trying to compute the mu star using, for example, this GW code. Yeah. But again, I mean, this is not my paper.
I think the problem is that if you're starting again, there is no way to this you to get close again and see at the time. At least with the problem start, with an problem start or realistic to interaction at this point.
Other questions? Don't you try school? Last question. I have one question. So all the results that you presented are amazing, but they were obtained with LDA and DGA functional, correct? So what is the roadmap of the CW project for advanced functions like meta-DGA, hybrid functionals, Hubbard, Koopmans? Because there are many materials out there with other elements like transition metal, rare earth, and in superconductors we have also like transition metal, 30 plus U or stuff like that.
The roadmap is very easy. We are following the development of QE more or less. So what we need, again, what we need to do this calculation is to start from this electron-phonon matrix element, right? And those are computed with the FPT, which in this case quantum espresso. And so, yeah. Okay, yes. So basically this object is computed with the phonon code. And so in principle, whatever is put there, it's not too difficult to extend that with PW usually. So the most difficult part is to have support for all these fancy functionals and so on. But once it's there, it's usually not too difficult. Yeah. So the plan is, I guess, to try to follow with some delay because it still takes time to implement it, but to follow whatever is available. But indeed, this is one way. And then something I'm particularly interested in is to go beyond and to go to the many-body framework and to actually compute the electron-phonon matrix element for GW. So you have something called GW perturbation theory. This is a work from Zheng Li and Stephen Louis. And there you can actually try to compute this using perturbation theory, but at the GW level. And that, in some material, is quite important to use this additional electron correlation. And so, yes, so in my group now, we are looking for trying to do something similar for semiconductor.
Yeah. So basically, the bottleneck is the phonon code of quantum stress. As soon as there are some advanced functionals there,
it's relatively easy, yes, in general, because basically you have to work well. What you get from quantum espresso is the change of potential. Then you have to reconstruct the element, but you can always reuse the routine from the phonon code. So if they're implemented, it's not very difficult to extend.
As far as I know, there is no roadmap to the phonon code.
That would be good to have one.
Because implementing, for example, hybrid functionals is extremely complicated, and no one wants to do it. It's really
I think this connects well with Tommaso's comment.
Sure. Two things. One is not only the matrix elements, but it's also just the conservation. So anything that changes the band dispersion. If you go to your previous expression for the Boltzmann equation, so that there will be two places where there is all those delta function.
Yes, I can comment on that.
We are doing the electron-phonon with finite differences again, not because we don't like in the response, but because doing it with the Koopmans of the hybrids, just very fast.
No, I mean, so I can also say that, okay, so you can do approximation. So instead of computing this object that's quite difficult at a higher level of theory, you can simply plug better phonon dispersion or better electron dispersion. So this is actually easy to do in EPW. So instead of Kohn-Sham band structure, you can simply put, or Kohn-Sham state, you can put GW state. So there is an input flag to read external eigenvalues. And so you can actually compute all of this at a GW level, but you're only changing the E. Yeah? So it's not fully consistent because the G will still be at the DFPT level, but you can update the eigenstate. And in principle, you can also update the phonons. So the EPW code can read an interatomic force constant. And so if you're doing a SHA or if you're doing TDEP or whatever, you can simply get your renormalized or changed phonons and you can plug them there. Now, this is not, so this can be done, but then if you want to go beyond and this is not done, you can also express this theory in a sort of Kubo-like form in which you have spectral function. In that case, you can plug spectral function both for the electron but for the phonons as well inside your formula, and that can be very important if you are very strong in harmonicity or things like that, where the phonon mode are not very well defined, and then you have sort of a crosstalk between all these phonon mode. And so one easy way is just to use the spectral function, because then you have very dispersive band, and then you can just talk to each other and you do the integral. So those are direction to go, let's say.
Any final question?
Okay, so these are
But just almost know that these different techniques so what's important to get right for these? So is it the band gap or the effective mass, or what, like if you go to some of it into everybody one particular function, or like what the
I have a slide for that if I find it. There you go. So this is not fully answering the question, but somehow. So this is for this, let's say 20 cases, 20 material, electron and hole. So here you see the impact on the mobility of different approximation, right? So in this case, I took the reference of the 0 as being the best one that I had, which was done, with whatever, with PBE and then quadrupole and so on. And then I tested sort of what is the change, relative error, but also absolute one, if you change something. So this is the sort of change that you are getting if you're changing potential, but not the exchange correlation. So I just tested, some libraries, and you can test different potential, pseudo-potential, let's say, but maybe with semicore, without semicore, things like that, but still the same exchange correlation function. And you can see that you have some changes, maybe, I don't know, 10%, something like that at most. So square are all mobility, circular electron mobility. If you change the exchange correlation function, so in this, if I remember, it was PBE, and then this was LDA, basically. So the change is even smaller somehow, because this is from the same pseudo-potential library. It seems to slightly underestimate the band. Then lattice is the difference between the relaxed lattice and the experimental lattice. Again, you have a sort of not too large spread. Now, septa is quite interesting. So this is when you neglect this second order term. This can be connected to neglecting backscattering and so on, if you connect that to the phonon transport. In that case, you almost systematically underestimate. So if you do the self-energy acceleration time approximation, this is very consistent. You will always underestimate. You do the full iterative solution, you sort of increase the mobility. If you neglect spin-orbit coupling, that's also very interesting. So spin-orbit coupling will typically not modify the conduction band, at least for the simple 3-5 semiconductor, but they will change the conduction band. So you get spin-orbit splitting of the degenerate manifold, and that has a big impact. Even in silicon, where you only have 43 MeV splitting, that has an impact because, again, what matters for transport is really the edge of the conduction, maybe like 0.1, 0.2 eV of the valence band maximum. So changing your bands there has a big effect. So you can see very big underestimation, and you can see that all the ones that change a lot are all the whole mobility, never the electron. So spin-orbit coupling is important for the whole mobility. And then, yeah, basically this is the effect of dipole and local velocity and so on. So this is, this is the effect if I'm using only a dipole and I don't use quadrupole and so on. And then this is the effect if I use an approximated velocity. So that maybe doesn't answer. I guess you wanted to know about hybrids and so on, but we didn't do the calculation for that.
Okay, thank you. Let's thank Manuel again.